All right, folks, let us continue on and get this day over with so y'all can go home, relax, and dream about elasticities. All right, so we're going to look at obtaining elasticities from our demand function. We've established the nature of the three elasticities that we're most interested in this class: the own price elasticity of demand, the cross price elasticity of demand, and the income elasticity of demand. All right, so let's say that the relationship between the quantity demanded and the variables that we're interested in is linear. So it takes the linear form. So if the demand function is linear and given by this expression here, where quantity demanded of good X is equal to some constant, alpha 0, alpha naught, plus the marginal effect of the price on the quantity demanded of good X times the price of X. So that's what alpha X represents. Again, it represents the effect of a 1 unit change in price on quantity demanded of X. Also, the effect of a change in the price of Y on the quantity demanded of good X, which is represented by alpha Y. So if price changes by 1 unit, how much is quantity demanded changed by? Well, alpha X, Y tells us that. And of course, the sign of that will tell us whether the goods are substitutes or complements, right? So if the price goes up and quantity demanded goes up, that means they're substitutes. If the price goes up and quantity demanded goes down, that means they're complements. Also, alpha M represents the marginal impact of income on quantity demanded. So if income goes up by 1 unit, quantity demanded goes up by 1 unit. If it's a normal good, or down by 1 unit. If it's an inferior good, if this number is equal to 1. So alpha M tells us that marginal effect of a change in price. And then H we talked about being either of the other variables that we are considering affecting demand, which we don't need to be specific about. So recall that the own price elasticity of demand is equal to this expression here, which we derive to be equivalent to this expression here, right? So it's the ratio of the percentages, which is also equal to the estimate of the slope of the demand function times the price over the quantity demanded, or the actual slope of the demand function times the price of the quantity demanded. Same thing. These are equivalent. This is from calculus, this equivalency. All right. Where the change in quantity demanded of good X with respect to a change in price of X is equal to alpha X. It's equal to this this variable here, right? I mean, this constant here. So we have the price of X, and if it changes by 1 unit, then quantity demanded of good X will change by however many units this tells us. This will be negative, representing the law of demand. As price goes up, quantity demanded goes down, and vice versa. So therefore, this is the slope. So if we just ignore these other variables for a second, and this is just the basic linear equation between quantity demanded and price, the demand function, then this is the slope of that line. So there, alpha X is this value here. And then, of course, the price of X is whatever the price of X is, and the quantity demanded of X is whatever the quantity demanded of X is at any particular point. So the elasticities are, we've got the own price elasticity of demand is equal to that alpha X times the price of X over the quantity of X. We've got the cross price elasticity of demand is equal to alpha Y, right? It's the derivative of the demand function with respect to the price of the related good, the price of Y. So that's going to be alpha Y here. And then you've got, from the elasticity expression, price of Y over quantity of X. And then finally, the income elasticity is equal to, again, that change in quantity demanded with respect to the change in income, which is equal to alpha M times income over the quantity of X. So you can get the information you need to figure out your elasticities from a standard demand function that we studied in the last chapter. So for a linear curve, the elasticity of demand with respect to a given variable is simply the coefficient of the variable multiplied by the ratio of the variable to the quantity demanded. So that is a relationship between the elasticities and the demand function of a linear demand function. Along these curves, the value of an elasticity depends on the particular price and quantity at which it is calculated, as we learned earlier. So again, our elasticities will change as we are moving along our demand and the price of the related good relationship, as well as the income to quantity demanded relationships. All right, so that is for a linear demand function, but what if we don't have a linear demand function? So managers frequently encounter situations where a product's demand is not a linear function of prices, income, and other demand shifters. Suppose the demand function is not a linear function, but instead is given by this expression here, where you've got some constant, and then you've got the price of X raised to the marginal impact of the price of X on quantity demanded of X, which is beta X, times the price of Y raised to its marginal impact, beta Y. We're just using betas instead of alphas here just to denote the fact that there's different, because this is not a linear demand function, it's a non-linear demand function. We've got income raised to its marginal impact on quantity demanded, and then we've got H, whatever it is, advertising, whatever, raised to its marginal impact. So that's an example of what a non-linear demand function could look like. It just depends on the market a firm might be operating in. C, of course, is a constant. So we could actually turn this into a linear function by taking the natural log of this equation. Taking the natural log of this equation, we obtain an expression that is linear in the logarithms of the variables. So this expression, if you take the natural log of each side, will get us to this expression here. And I'm going to show you how to get from that point to this point in a second. Where in this case, beta naught is equal to the log of our constant, but our constant is a constant, so whether it's the log of a constant or a constant, it doesn't matter, so we just call it beta naught. And then we see that we've got the beta x in front of the log of px, and that's the same form that we have for all the other variables. So this relation is called a log linear demand function. All right, quick review of logarithms. So the logarithm of x to the base of b is the number y satisfying. So you've got some number that's being raised to some exponent y, and that's going to give you some value, right? So the log of b, the log of x with the base of b. So essentially what this is asking is like, what does the base need to be raised to in order to get us to x? So the logarithm function of x, so the log with base of b of x is equal to y, right? So that's basically taking this, it's what's called the inverse function of what's called an exponential function. So you've got some number b being raised to some exponent that gets us to x in the exponential function. And then the log version of that is you have the log of this number x base b, and it's asking what do you need to raise b to get x, right? So the log of base b to x. The log of x base b. However you read it, whatever, it doesn't matter as long as you understand what this means. So the exponential form, let's say you have 5 squared equals 25, right? So essentially, the log form of this is you need to figure out what do you need to raise 5 to get 25. So it's going to be the log of base 5. The log of 25 base 5 equals 2 in this case. So what do you need to raise 5 to get 25? That's going to be the log of 25 base 5. If you have a base of the number e, which is it's kind of like one of those mathematical constants like pi. I want to explain it, but just understand that there is this number e that has like meaning in math. It's a lot. It would be a lot to explain. I'm not going to explain it here. But if you have a log with a base of e, we refer to that log as a natural log. Or we can call it just the log function, and it's denoted as ln of x. So when you have a log with a base of e, you just describe it as ln of x. And e is this mathematical constant here. You don't need to know this number. And this stuff is just review log stuff, so it's just meant to help you understand how we get from that nonlinear demand function to the log linear demand function. I won't expect you to be able to do it though, but you should understand it because logs are very common in business. They're used all the time. You need to understand what they are and how they work, their properties, etc. All right, and also understanding the log linear form of our demand relationship will help you to understand how to easily get elasticities from your data. All right, so relevant properties of logarithms are, so let's say you have the log of some number that can be broken down into the product of two other numbers with a base of b. That's going to be equivalent to the log of m base of b plus the log of n base of b. So you can decompose this log into this expression here. So if you have the log of two numbers that are being multiplied, it's equivalent to the log of one of those numbers plus the log of the other number, same base b. If you have the log of some number n raised to some power r with a base of b, that is equivalent to the log of m with base b times that exponent. So you can bring that exponent out, and these two expressions are equivalent, properties of logarithms. All right, so that's the end of the quick review of logarithms. All right, so let's go back to our elasticities for nonlinear demand functions. Suppose the demand function is not a linear function, but instead is given by this expression here. If we take the natural log of this equation, again, we're assuming a base of e, right? So we don't even think about that. When we hear the term natural log, we know we're talking about ln of whatever, and we're not thinking about the base. We just know it's the natural log, ln. So we obtain an expression that is linear in the logarithms of the variable. So we take the ln of both sides. So ln of q dx equals ln of that entire expression there. We know that from our properties of exponents that taking the log of the product of a bunch of terms can be decomposed into the sum of the log of each of those terms, right? So this is equivalent to this term here where we take the log of c plus the log of p of x raised to the beta x plus the log of this term, plus the log of this term, plus the log of this term. And that's how we get from here to here. And then one last manipulation here, using the properties of exponents. If you have a log of something raised to some power, that's equivalent to that power times the log of the something, right? So this term here becomes beta x times ln of px, and so on and so forth. We have the log of a constant. We don't know what that constant is. It's a number. We're taking the log of a number that's not changing, that's very generic. So we'll just think of it as just some other number. So we'll use beta naught to represent that constant and not worry about logs with that term. It's just some value. And then we've changed the form of our expression now into one that will provide us the information we need really easily, just using the properties of exponents, of logarithms. All right, so that's how we get from this expression for this nonlinear demand function to this log linear demand function. Is there a question? No. Feel free to ask questions anytime, folks. All right. So again, beta naught is equal to ln of c. So again, this relation is called a log linear demand function. When the demand function for some good x is log linear and given by this expression here, the elasticities are really easy to get. So the own price elasticity of demand is just the coefficient on the log of the price. So beta x is the own price elasticity of demand. The cross price elasticity of demand is just the coefficient on the log of the price of y. So beta y is the cross price elasticity of demand. And the income elasticity of demand is just the coefficient on the log of income. So instead of having to do the linear thing where you get the coefficient, then you multiply by the price divided by the quantity to get the own price elasticity of demand, if you turn your expression into logs and then are able to estimate these, you can just get the elasticities that way very easily. And I'll show you how that's done in a second. So notice that when demand is log linear, the elasticity with respect to a given variable is simply the coefficient of the corresponding logarithm. All right, now let's find out exactly how to get this information via regression analysis. All right, so the preceding analysis assumes the manager knows the demand for the firm's product. So we've assumed thus far that like this information, these equations that we see with numbers, they already have the information. They don't need to find it. As a manager, though, you may obtain estimates of demand and elasticity from published studies or from consultants hired to estimate the demand function. Another option is to enter data into a spreadsheet program like Excel, click the regression toolbar to obtain an estimated demand function along with some regression diagnostics. So on Excel, you can run a regression really easily, but it's like a hidden function. You have to turn it on. So if you just do a Google search, how do I run a regression in Excel? And then it tells you, oh, go to settings, and then say, yeah, I want to use this, and then it pops up in the toolbar, and then you can use it. I don't know why that is the case. It just be there, but whatever. Just know that you can activate it, and that there are other hidden features to Excel you don't even know about. Super powerful program, Excel. They're like super powerful. All right. So regardless of how the manager obtains the estimates, it's useful to have a general understanding of how demand functions are estimated and what the various diagnostic statistics that accompany the reported output mean. So that's what we'll cover here. So again, this entails knowledge of a branch of economics called econometrics. Econometrics is the statistical analysis of economic phenomena. It's beyond the scope of this course to teach you how to estimate demand functions, but it's possible to convey the basic ideas econometricians use to obtain such information. Gesundheit. I do recommend taking an econometrics course just to kind of understand how all this stuff works. All right, so let's briefly examine the basic ideas underlying the estimation of the demand for a product. Suppose that there's some underlying data on the relation between a dependent variable, y, and some explanatory variable, x. So quantity demanded can be y, explanatory variable can be the price. Let's say we have a bunch of data points that correspond to price-quantity combinations. So we have this point here, we have this point here, B, C, D, E, F. So just information you got from like markets, different areas. How much are people buying at this price? How much are people buying at this price? How much are people buying at this price? All right, there. In this case, I have five data points, 5 datums as they're called. And they're plotted there. So the points A through F do not lie on a straight line or even a smooth curve. So there isn't a clear, like, mathematical relationship between these points. They're just a bunch of points. The job of the econometrician is to find a smooth curve or a line that does a good job of approximating the relationship that's embodied in these points. So we can see that like this point represents a high amount of quantity demanded, let's say. So in this abstract example that I'm tracking here, quantity demanded is on the y-axis and price is on the x-axis. Just run with it while it's very general for now. Anyway, so we see that I'm sorry, price. Let's just say price and quantity. Just do it the normal way. So price is over here, quantity demanded is here. When price is high, quantity demanded is low. We see that as the price goes down, quantity demanded increases. So even though there isn't a clear like linear relationship between the variables, we can see that there is a negative relationship there. Right? We don't exactly know what that looks like. We don't know if it's like an exponential relationship or a quadratic relationship or a linear relationship. We don't know that. But what we do know is that as we move from left to right and price is going down, quantity is increasing. Quantity demand is increasing, just based on these like data points. So suppose the econometrician believes that on average there is, let's say, some linear relationship between y and x, but there's also some random variation in the relationship. Even though the points don't necessarily like fall onto a line, they kind of approximate that negative relationship that can be approximated by a line with a negative slope. And then there's some error, meaning that there's going to be some distance from that line of each point, which we can call the error for each of those points. This sort of the amount that the points are varying from the relationship that we think exists there. So mathematically, this would imply that the true relationship between y and x is some linear relationship, right? Y equals some constant plus some slope times x plus some error. So each quantity will have some marginal effect. If you add it to the constant, that'll get you to the price. But there will be some error in that relationship. So the line may estimate a value y, and then the e represents the distance from y that the point actually lies. So there's some error between what the relationship can estimate versus what we actually have observed. So A and B are unknown parameters. So A and B are things that we don't know. We don't know what the constant is. We don't know what the slope of the line is. And E is, again, some random term, which we call an error term. And we assume when we're doing regression analysis that it has a zero mean, meaning that on average, those errors will sum to zero. So some of the points will have a positive error. Some of them will have a negative error. If you add all that together, they will sum to zero. Right? So we assume that there's a zero mean there. On average, it will be zero. So the econometrician has to find out the values for A and B. So we have to then be able to estimate these parameter values to give us the best estimate of that linear relationship that fits this data that sort of floats around this imaginary line that we think exists there. So the econometrician uses a regression software package like Excel to find the values of A and B that minimize the sum of the square deviations between the actual points and the line. So it looks at the distance between the point and sort of the line that we're looking to estimate, and the line represents the minimum amount of distance between all the points and this like hypothetical line that we believe exists there. In order to actually get that line, and the process of doing it involves calculus, and the steps are shown in an econometrics course. You know, it's fairly rigorous. It'll take a whole lecture just to show you how to do that. I'm not going to do that here. It'll just confuse you and will make you angry probably. But you should know how it works. You should take econometrics. But anyway, that's what a regression is doing. It's minimizing the sum of square deviations. So it's getting us this line that minimizes those square deviations as much as possible. So that line that is estimated via this process is called the regression line. It's the line that minimizes the square deviations between the line and the actual data points. So these values of A and B, which we estimate, are denoted A hat and B hat. They're called parameter estimates. So we put that little hat on top of it just to kind of signify that they are the estimated values of those parameters and not the actual parameters. And the corresponding line is known as the least squares regression. So the least squares regression line for this relationship is going to then be equal to this expression here. So the error we assume has a zero mean, so it drops out, and what we're left with is the equation for a line, which we have estimated based on these points that don't necessarily fall in the line, but this is the best line that we can figure. It explains the relationship between x and y. So the parameter estimates represent the values of A and B that result, again, in the smallest squared errors between the line and the actual data. All right, so to illustrate, suppose that a television manufacturer has data on the price and quantity of TVs sold last month at 10 outlets in Pittsburgh, let's say. So 10 different areas in Pittsburgh. They looked at prices and quantity sold, and again, simple reflection of the law of demand. As price goes down, quantity demanded goes up, and vice versa. They're not in order here. Let me see. This one goes down. No, they're not in order, descending order. So, I mean, the relationship is there. It's just not ordered. But anyway, these are 10 datums, 10 price quantity combinations observed in the Pittsburgh area for the TV market. All right, so suppose we did a regression. So you would just go to Excel and you would go to your toolbar and you would say regress column B on column C. So basically saying that B is the dependent variable and C is the independent variable. And then you would get this kind of a printout or readout. All right, so the intercept, so down here we're going to have estimates of our coefficients. So the intercept for the line, A hat, is going to equal 1631.47 for TVs, basically telling us that the quantity demanded of televisions is 1,631.47 units independent of price. So because we haven't included these other variables to explain the price, the quantity demanded, we only included price, that there is some quantity demanded that's independent of the price. It is a constant, right? And so if you were to throw the other variables under, the income, the price of related goods, the advertising, everything else, then this number would go down because some of that would be explained by these other variables. All right. The estimated coefficient of beta hat, the slope parameter, is in this case negative 2.6. So that's basically telling us that as the price goes up by $1, quantity demanded goes down by 2.6 units. All right, so the estimated linear demand function for TVs that minimizes the sum of squared errors between the actual data points and the line through the points is thus given by this equation here. So this is our regressed line here. Here is our estimated demand function. All right, so essentially here are all those points. Here is the regression line that minimizes those errors, and there is our estimated relationship. The thing about this expression, though, is that it reflects the data. It reflects like these 10 or whatever data points we have. And the question is, like, does the estimated relationship that reflects that data predict how that actual relationship looks in nature? So if we were to do an analysis of all TV markets anywhere, would the actual impact of the price on quantity demanded be negative 2.6? Would the constant be 1631.47? Or would that change depending on whether you're using 10 data points from New York, 10 data points from Moscow, 10 data points from wherever? So then the other numbers that you saw on that table are diagnostic statistics that kind of give you an idea about how good of an estimator of the actual relationship this estimated relationship is. So we'll go through them and sort of look at their various properties. All right, so the table provides information about the precision with which the parameters of the demand function are estimated. So again, here are our estimates for the intercept and for the coefficient on price. The coefficients reported, again, are merely parameter estimates of the true unknown coefficients. The true unknown coefficients are the actual numbers that we know exist in the world, right? If you were to do a survey of every single market in the entire world for televisions, or in the United States, wherever you're interested, then there will be some marginal impact of price and quantity demand, and there will be some constant. So again, the coefficients are merely parameter estimates of those true unknown coefficients. So given, again, different data generated from the same true demand relation different estimates of the true coefficients would be obtained. This column tells us the standard error. The standard error of each estimated coefficient is a measure of how much each estimated coefficient would vary in regressions based on the same underlying true demand relation, but with different observations. So again, it tells us how precise is our estimate. Well, this standard error for our coefficient tells us that it would vary, relatively big amount, 243.97, given, repeated sort of analysis from different data. Price, though, would not vary that much, but relative to the amount, a decent amount. The smaller the standard error of an estimate coefficient, the smaller the variation in the estimate given data from different samples of data. So given a set of standard but somewhat technical assumptions about the regression model, which we won't go through here, but you will learn in econometrics if you take that class, which you should. So given some assumptions about the regression model, data sampling, and means of the error, so averages of the errors, the least square estimates, these estimates that we got from our least squares regression are unbiased estimators of the true demand parameters, meaning that they are not biased to the data. They are unbiased. They do represent a more universal sort of understanding of that relationship that we're studying. Even though they're not exactly what it is in nature, they are the best we can do given what we have. All right. We can sort of figure out where the actual values might lie in reality, in the actual markets that we're interested in, via what are called confidence intervals. So given a parameter estimate, its standard error, and some necessary technical assumptions, which we won't go through here, the firm manager can construct a lower and an upper bound on the true value of the estimated coefficient by constructing a 95% confidence interval. The coefficients reported are merely the parameter estimates of the true unknown coefficients. So here is our rule of thumb for the 95% confidence interval, which is a principle here. So if the parameter estimates of a regression equation, let's say our A hat and B hat, which are these two here, so our intercept is our A hat, our price coefficient is our B hat, then the 95% confidence intervals for the true values of A and B can be approximated by, for A hat, it's going to be plus or minus 2 times the standard error, which is represented by sigma A hat subscript A hat. So standard error can be denoted by this sigma, which is again another Greek letter. The Greeks had weird letters, but to them we have weird letters. So by taking our intercept, adding twice our standard error, we will get the upper bound on our confidence interval, meaning that we are 95% sure that the actual value of our intercept is going to be, in this case, 2194.07. And if we subtract 2 times our standard error from our coefficient, then we are 95% sure that the actual value of our intercept will be at least 1068.87. So we are 95% confident that the actual value of this intercept that exists in the world beyond just our simple little data set is going to be somewhere between 1068.87 and 2194.07. So our confidence interval, again, gives us that information, which we get from the regression diagnostic statistics, specifically the coefficient estimates and the standard error. Again, we can do the confidence interval for our price coefficient, which we've estimated to be negative 2.6. If we add 2 times our standard error of 0.53, we get negative 1.37. And if we subtract 2 times 0.53, our standard error, again, denoted by sigma subscript B hat, then we will get negative 3.82. So the actual impact that price has on quantity demanded in all television markets is likely going to fall with 95% confidence between negative 3.82 and negative 1.37. Any questions about this? So with this stuff, like, it's important. Just what I expect you to know is, what they mean, and like, so here I would expect you to know this, like how to be able to calculate the upper and lower bounds for the confidence intervals, and as I go through, I'll highlight the things that I expect you to know. So again, these are the standard errors of A hat and B hat. All right, so for instance, again, the table indicates that the upper and lower bounds of the 95% confidence interval for price are these numbers here. The parameter estimate for the price coefficient is negative 2.6, which lies exactly in the middle of them. From this information, we know the best estimate of the price coefficient is negative 2.6, and we are 95% confident that the true value lies somewhere between those upper and lower bounds. All right, now we have some other diagnostic statistics here that can give us a little bit more ideas about how precise our estimates are. So the first one is our t-statistic in this column here. There's a t-statistic for each of our estimates. So the t-statistic is the ratio of the value of a parameter estimate to the standard error of the parameter estimate. So if the parameter estimates are A hat and B hat, and the corresponding standard errors are sigma A hat and sigma B hat, the t-statistics for A hat, so for that intercept estimate, is going to equal the ratio of our estimate to its standard error, and that will give us our t-statistic. And the t-statistic for our price coefficient is equal to our estimate of the price coefficient divided by its standard error. All right, so when the t-statistic for a parameter estimate is large in absolute value, then you can be confident the true parameter is not zero. So if the t-statistic is large enough, then you can be confident that in reality, beyond our little data set that we have, let's say we're talking about price, the impact of price on quantity demanded is valid. It's not zero, meaning that price doesn't have no effect on quantity demanded. There is actually an effect of price on quantity demanded, and we know that based on our t-statistic. We also know it based on the law of demand and everything we've been learning, but again, you can study the relationship between any variables and sort of try to figure out the statistical significance of one variable on another via this method. So if the t-statistic is large enough, then it tells us that the impact of price on quantity demanded is statistically significant. That's how we describe it. We say it's statistically significant. So again, you can use this method to test the significance of any variable's impact on some other variable. It was a large part of what I did in my dissertation. I took a bunch of variables that I didn't know would impact the variable I was interested in studying, and I did a bunch of regressions, and I figured out stuff, and I wrote a book based on it. All right, so again, if the t-statistic is large enough, then you can be sure that the true parameter is not equal to zero, meaning that there is some impact of that variable on the dependent variable. So the reason for this is that when the absolute value of the t-statistic is large, the standard error of the parameter estimate will be small, right? It's the ratio of the estimate to the standard error. So if the t-statistic is large, that means that your estimate is being divided by a smaller number, which means that there's a small amount of variation in the number that you're looking to estimate, right? So if the standard error is small, that means that there's a decent amount of precision in your estimate. And if that standard error is small, your t-statistic will be large, which means that your your estimate of this variable is statistically significant. So that therefore that variable is a valid explanatory variable, a variable that does explain some of the variation in the dependent variable, in this case, quantity demand. So one can be more confident that given a different sample of data drawn from the true model, the new parameter estimate will be in the same ballpark. So if if let's say price is statistically significant because it has a big t-stat, which it does in absolute value, and absolute value is what matters. And so does the intercept here. Then what that tells us is that if you were to do the same analysis with different data points, you would find the same kind of like statistically significant relationship. That indeed this variable does have an impact regardless of what data you're using. Regression packages also provide p-values, which are much more precise measures of statistical significance. Basically, they represent the probability that the significance you find is false. So a 0.0012 p-value means that there's only a 12 in 10,000 chance that the true coefficient of price is actually zero. That in reality, in all the data of all price quantity combinations for all TV markets, there's a 12 in 10,000 chance that price has actually no effect on quantity demand. So there's a ridiculously small chance that that's the case, meaning that our estimate is, again, reinforced to be statistically significant. When p-values are 0.05 or lower, they're considered low enough for a researcher to be confident that the estimated coefficient is statistically significant. If the p-value is 0.05, we say that the estimated coefficient is statistically significant at the 5% level. Notice that the p-value reported for the coefficient of price, in this case 0.0012, implies that it is statistically significant at the 0.12% level. The estimated coefficient is highly significant, as we would think given what we know about price and quantity. So that brings us to this rule of thumb for using t-statistics. When the absolute value of the t-statistic is greater than 2, the manager can be 95% confident that the true value of the underlying parameter in the regression is not 0. So I would need you to understand what a t-statistic is, the ratio of the parameter estimate to the standard error, and then I would also need you to know the rule of thumb for it. The fact that if it is greater than 2, then we can essentially say that the estimate is statistically significant. All right, so we also have other diagnostic statistics that give us ideas about the overall fit of the regression line. We included quantity demand, we included price as the only explanatory variable on quantity demanded. So we can look at statistics that tell us how good of a fit is that for this relationship. Is it good? Did we leave too many things out? Is it enough? Other statistics will give us ideas of that. So in addition to evaluating the statistical significance of one or more coefficients, one can also measure the precision with which the overall regression line fits the data. So two values frequently used to measure the overall fit of the regression line is the R-square and also what's called the F statistic. So we'll look at each of them in turn. Let's look at the R-square first. So the R-square, also called the coefficient of determination, tells the fraction of the total variation in the dependent variable, in this case quantity demanded, that is explained by the regression. It's computed as a ratio of the sum of squared errors from the regression to the sum of squared errors. So there's a certain amount of variation in the quantity demanded that we observed in our data, right? We can add them together, get an average, and then look at how much each point is deviating from that average. and that'll tell us how much overall variation there is in our dependent variable. We can also use our estimated line, plug in our prices, see what the estimated line tells us is what the quantity demanded should be, get an average of that, see how much all the points are deviating from that. That is the squared errors from the regression. So that's the variation, the sum of squared errors from the regression. That's how much variation the model is predicting. And then the total sum of squared deviations is the actual variation that we see in the data. So then the question is, how much of the variation in the actual data is being explained by the variation in the model? And that's what the R squared can tell us. So it's the ratio of the explained variation to the total variation. So you've got the regression sum of squares over the total sum of squares. If the R square is equal to 0.75, let's say, it means that the estimated demand equation explains 75% of the total variation in TV sales across the sample of 10 outlets. So again, that is telling us that a lot of the variation in the dependent variable is being explained by the model. So it's a decent fit. Including just the price helps us to explain a decent amount of variation. But if we were to include the price of related goods, income, amount spent in advertising, etc., that'll explain more of that variation in the actual quantity demanded. And so it would be a better fit. You'd get a higher R squared. The value of an R squared can range from 0 to 1. The closer R squared is to 1, the better the overall fit of the estimated regression equation to the actual data. There's no simple cutoff that can be used to determine whether an R squared is close enough to 1 to indicate a good fit. So there isn't just a rule of thumb that applies to any regression. It depends on what regression you're doing, what you're studying. So let's say you're studying time series data. Time series data is like data on one variable over time, right? So you can look at GDP, the output in an economy, over 20 quarters or something, 5 years. So if you're doing that, R squares are often in excess of 0.9. If you're looking at cross-sectional data is like you're looking at how a bunch of variables are affecting one variable in one moment of time, and then you're saying, well, how is that relationship changing over time? So you've got a cross-section in a period, and then sorry, I'm talking about panel data. I'm getting more complicated than I need to with you guys. I shouldn't do that. Cross-sectional data is just looking at one moment in time and saying, at this moment in time, how is quantity demanded being affected by price in this time, which is what we did in this example. We did a cross-sectional analysis. So with cross-sectional data, R squares below 0.2 are not uncommon. So it just depends on like what is being studied, and if you kind of like understand like the volume of work that's been done in that area, and you can kind of tell like what R squares are like in other works, and then you can kind of gauge how well your R square is telling you how good the fit is in comparison to work that's already been done. So again, it depends. Like there isn't a rule of thumb for the R square. A major drawback of the R square is that it is a subjective measure, as I mentioned, of goodness of fit, because again, there isn't a rule of thumb. It's subjective to whatever you're studying. So you can't have like general rules about the values and what they mean. Another problem with the R square is that it cannot decrease when additional explanatory variables are included in the regression. So you can start just throwing a bunch of variables into a regression relationship, and your R square will increase. So it'll seem as though you're doing a better and better job of explaining, how one variable is affected by other variables just by throwing more variables into your regression. So again, if we included income, advertising, other explanatory variables in our regression, but held other things constant, we would almost surely get a higher R squared. Eventually, when the number of estimated coefficients increased to the number of observations, we would end up with an R square of 1. Sometimes the R square is very close to 1, merely because the number of observations is small relative to the number of estimated parameters. So for this reason, many researchers use the adjusted R squared. So the adjusted R square is equal to 1 minus 1 minus the R square times the number of observations minus 1 over the number of observations minus the number of parameter estimates. Don't worry, you won't need to know this equation. You just need to understand that there is an R square and that there's reasons why it's not great, and that there's an adjusted R square, which is meant to sort of, kind of fix the problems of the R square. So in this case, n is the total number of observations, and k is the number of estimated coefficients. So in performing a regression, the number of parameters to be estimated cannot exceed the number of observations. So, so again, like in order for the regression to even work, you have to have at least as many datums, like data points, as number of coefficients being estimated. If you have more coefficients than data points, then the regression will be worthless. All right, so this is our expression for R square, and the reason why it's better than that for adjusted R square, the reason why it's better is because it actually brings down the R square as you add more explanatory variables, where again, when you added more to the normal R square, it goes up just mathematically based on the way that it is estimated. So here we've got n minus k. The difference represents what's called the residual degrees of freedom after conducting the regression. So it basically tells us how much more data we have than parameter estimates, how much freer are we to sort of have confidence about the power of our estimate. All right, so notice that the adjusted R square penalizes the researcher for performing a regression with only a few degrees of freedom. That is, estimating numerous coefficients from relatively few observations. So as your parameter estimates go up, so you have some number of observations minus a bigger number, then you're going to get a smaller number down here, which means you'll have a number divided by a smaller number, which will be a bigger number. So then you'll have 1 minus a bigger number, which means that our adjusted R square will be smaller. So as you increase the number of parameter estimates, that will hurt your R square, which fixes the problem, your adjusted R square, which fixes the problem with the R square. Anyway, these are important statistical issues that you probably don't care about too much. But really, like, you have to be super precise with these methods. You can't just like throw things out there and say, oh yeah, it works, but it actually doesn't work. Well, if something doesn't work, you need to fix it, and it has been fixed. But still, you can throw in the R square, and there it's always estimated for you. Just to kind of get an idea of things. And then the R square, if it's close to it, you know that everything's fine as far as like, the amount of estimators that you put in there, and the overall goodness of fit is consistent. So again, here we have an R square of 0.75, adjusted R square of 0.72, and that's basically telling us that the amount of variation explained by our model is roughly 75%. And it has nothing to do with the fact that, we have X amount of variables in there to explain our variation in quantity demanded. So in our example, we have n equals 10 and k equals 2. For these data, there's little difference between the R square and the adjusted R square, so it does not appear that the high R square is a result of an excessive number of estimated coefficients relative to the sample size. Just understand what R square is overall as far as like why you would use it, to understand the goodness of fit. Understand that it's imperfect because it's subjective, and also if you add more variables, it goes up. And so understand that there's an adjusted R square that's meant to fix that problem. But you will get both of those in a regression analysis printout that, again, provides you diagnostics on the precision of what you have estimated. All right, there's an F statistic as well. An alternative measure of goodness of fit is the F statistic. So in this case, our F statistic is 23.94. And what's good about the F statistic is that it also carries this value that tells us the statistical significance of that F statistic. So the F statistic provides a measure of the total variation explained by the regression relative to the total unexplained variation. The greater the F statistic, the better the overall fit of the regression line through the actual data. The primary advantage of the F statistic stems from the fact that its statistical properties are known. Thus, one can objectively determine the statistical significance of a reported F value. Just like you can look at the statistical significance of the coefficient estimates via the t-statistics and the p-values. So the low reported number in the example means that there's only a 12% chance that the estimated regression model fit the data purely by accident. So that's what that statistic is telling us. So it's telling us that our F statistic is a valid one, and that the amount of variation we understand it to reflect as far as what's being explained is a valid one. So again, it's just another statistic thrown in there to provide more sort of evidence for precision of what you have done. These things are really important because the actual methodology used to do regressions is contentious. There are assumptions that are made that could be debated about. Like I mentioned, that there are assumptions about the data, there's assumptions about how the whole thing works that allows us to say this works and everything I just said matters. But others can come in and say, wait, hold on, in the way that we actually estimate regressions, in the math that we use to kind of get to that line, there are problems with that. And so that's why you need as much evidence as possible to be able to back up your results. And that's why ultimately a lot of this work, even though it is valid and can provide you good insights, can also be contentious. People can debate the legitimacy of what you do with this kind of work. And that's why it's a tool, and it's meant to support an argument that you might make about, what's happening in your market or whatever. Generally, when it's something really simple like, demand analysis, it'll be very clear. But sometimes you're trying to understand the relationship between variables that hasn't been established before, that you maybe have an intuition about. You do some research, you get some data points, you do some analysis, regression analysis, you get some results. It says it's statistically significant. You write a paper saying, hey, this is a valid thing that nobody's observed before. And then, somebody will just come in and call into question the entire methodology you use. And so you need to be able to kind of back up what you've done as much as possible. And that's why there's all sorts of like these diagnostic statistics that come with regressions. And so it's important to kind of understand them, at least the ones that I'm highlighting here. I won't ask you to estimate confidence intervals. Just understand what a confidence interval is. Understand like what a p-value is. That probability that the estimated coefficient is actually 0 in reality versus what we actually saw. It was like 0.0012 in the table we saw for the estimated price coefficient. Anyway, just like you don't have to know everything. Just kind of understand these things like generally. I'm not going to be very precise about asking you like a lot of this stuff. None of this stuff will be in like the open-ended questions. It'll be in like multiple choice, if any at all. So just kind of understand like how they work, what they mean. You can go through the practice exams to kind of look at some questions that kind of reflect this information so that you have an idea of like, what you need to know. Because this is not a statistics course, but it's important for you to understand how these things work. It's important for you to understand how anything you use works. Don't ever just use things blindly. Don't ever go to a job and just start doing things and not think about like, what am I actually doing? You always want to know, because if you don't know, then you don't know anything. You don't really know what you're doing, and then you can't really move forward, like because you're just a drone. So think about what you're doing. Think about the tools you use. All right. Anyway, as with the p-values, again, we're looking at the significance of our F statistic, which is another means of sort of gauging the goodness of fit of the model. How good did we specify this relationship between quantity demanded and price? Should we have thrown in other variables? Well, quantity demanded can be explained by price pretty good. We don't necessarily need a lot. It explains it decently, and the fact that this tells us it explains it decently is statistically significant, meaning that if we did the same kind of analysis with other data, we would get a similar F statistic because it's a good fit for this relationship, this regressing price on quantity demanded. So as with the p-values, the lower the significant value of the F F statistic, the more confident you can be of the overall fit of the regression equation. Regressions that have F statistics with significance values of 5% or less are generally considered significant. All right, so I just did a regression for a linear expression, but I did mention you can get elasticities from the log linear expression pretty easily by looking at that coefficient. So you can estimate log linear versions of your relationship as well. It's really simple. You get your data, you've got price, you've got quantity, and you just use Excel and say, for this column, make a new column of the log of these quantities, and then the log of these prices, and then regress the log of the quantity on the log of price, right? And then you've got that log linear regression, and then the estimated coefficient will be the elasticity that you're looking for. So again, the techniques to estimate a linear demand function with a single explanatory variable can be used to estimate nonlinear demand functions. These same tools can be used to estimate demand functions in which the quantity demanded depends on several explanatory variables as well, such as price, income, advertising, and so on. You just throw them in and say, regress quantity demanded on all of them, not just the price column. Regress it on the price column, the price of related goods column, the income column, the advertising expenditure column. So for nonlinear functions that maybe aren't aligned but have like this kind of a curvature, actually this is how a log linear demand function would look. So here it appears that the price quantity are not linearly related. The demand function is a curve. The log linear demand curve we examined earlier in this chapter has such a curve shape. So again, you might have a bunch of data points, and then this log linear line curve is the best estimate of that relationship, minimizing the sum of squared deviations from that line. So to estimate a log linear demand function, the econometrician takes the natural log of prices and quantities before executing the regression. So then you'll get, again, the log of our quantity demanded equals some constant plus the coefficient that you've estimated. This has been estimated as well, plus the log of P. So this is the actual relationship that exists with the error, and then you can use procedures identical to those described earlier and regress the ln of Q, the transformed quantity, and p-value to obtain parameter estimates. So recall the resulting parameter estimate for beta p, in this case, is the own price elasticity of demand, since this is a log linear demand function. So again, if you regress this relationship, you will get the own price elasticity of demand to be this coefficient here. Multiple regression, again, you can use the same technique, throwing in other variables, not just one variable. So regression techniques can also be used to perform multiple regressions of a dependent variable on multiple explanatory variables. For the case of a linear demand relation, one might specify the demand function as this relationship that we looked at earlier, where we threw in the price of related goods, the income, and advertising. Where the alphas are the parameters to be estimated, so we would estimate the constant, we would estimate all these alphas as well. And E is a random error that has a zero mean. So provided the number of observations is greater than the number of parameters to be estimated, so you need more observations than in this case 1, 2, 3, 4, 5 parameter estimates that you're going to. So as long as you have at least 6 data points, one can use standard regression packages included in spreadsheet programs to find the values of the parameters that minimize the sum of squared errors of the regression. The R square, the F statistic, the T statistics, and confidence intervals for multiple regressions have the same use and interpretation described earlier for the case of a simple regression with one explanatory variable. So everything from the simple case translates to the more complicated case. Quick caveat, you now know how to interpret the output of a regression, how to use the output to summarize the demand for a product in a simple equation. Demand functions are not fictitious textbook constructs. They are equations that managers may actually obtain by using appropriate econometric techniques and data, not just a bunch of equations meant to torture you. This is actual practical information that will really help you and helps businesses every day to flourish. But it's important to stress that econometrics is a specialized field of economics that takes years of study to master. So even if you've taken the introductory econometrics course, that is just kind of giving you an idea of how econometrics works. It really goes a lot further than that. It's a super powerful tool, and if you can master it, you can be a master of this universe. You really can. But it takes a lot of work and a lot of study. Unless you've invested the coursework required to master a host of econometric issues that are beyond the scope of any managerial economics textbook or spreadsheet program, it is probably best for you to use your econometric knowledge primarily as a tool for communicating with an actual econometric specialist. But again, you can use this very practical approach to study minimal amounts of data and relationships that you're interested in if you're running a small business and you're maybe interested in some of the information that you can get from this kind of approach. All right, folks, congratulations. You survived a third lecture in this course. I'm going to open up the homework and the mini paper. They will be due at the middle of next week. And I'll also open up Chapter 4's homework so you can start working on all the homeworks that you'll need to get done before the first exam. I do, like I said, recommend you start getting ahead yourself and start preparing for the exam earlier rather than later. It will be good for you. Regardless, have yourself a great weekend, and I will see you next Tuesday.